My name is Ta Wang, and I'll be presenting my paper, High Precision Open World Website Fingerprinting. So what is website fingerprinting? In website fingerprinting, we're studying a client who is sending resource requests and resource data across this unsafe danger zone. In this danger zone, there exists local eavesdroppers who are, for example, ISPs, agencies and organizations who may be privy to information from those ISPs, packet sniffers, and so on. Such eavesdropper Eve is trying to identify what this web user is doing, which web page he is visiting on the internet. Now, of course, by default, the internet is not very secure against such a eavesdropper. Such a user would be revealing his source IP, destination IP, packet time, packet direction, and packet contents. So the source IP would reveal who he really is. The destination IP and the packet contents would reveal what he's doing on the internet. If we really want to protect a user's privacy on the internet, we should be using something like Tor. So in this anonymity network, if the attacker is a local eavesdropper, meaning that the attacker is close to the client, then the attacker can still see his source IP, but he won't be able to see his destination IP, which is what he's doing, because it's going to show up as the Tor onion node's destination IP. And also he won't really see the packet contents because the channel is encrypted. So this is how Tor protects your privacy, but when we consider website fingerprinting, which is an attack against anonymity networks like Tor, then what we're doing here is, given the remainder of this information, the packet time and the packet direction, and also the packet sizes, we're going to reveal what this person is actually doing. We're going to recover that, therefore compromising the privacy guarantees he had under Tor. So the reason why this works is essentially because websites are structured differently. At its most basic level, if you have a very large website, of course, the packet trace would be longer, but also because of how browsers load web pages, which is quite logical, it turns out that web pages have quite unique patterns which can be distinguished from each other. So another way to rephrase the website fingerprinting problem is, given a packet trace, which only includes the time, direction, and sizes, determine which web page the client has been visiting. So since this is a classification problem, we're going to use classification methods to solve them. But it does have two unique challenges. The first is that we need to solve it as a multi-class problem, because if you imagine what the attacker is doing, the attacker wants to distinguish between different web pages. If each web page is a class, then the attacker needs to distinguish between them, so it's a multi-class problem. But it also is a problem with a huge open world. The set of pages the attacker wants to classify is going to be far fewer than the total number of pages, which is going to be literally in the billions. So there's a bit of tension between those two challenges. The usual way to deal with a huge open world is to solve it as a binary problem, but since we have to solve it as a multi-class problem, sometimes we just define the open world as an extra class, but that creates, for example, class size bias. Another way to look at this is we need to be able to answer, is this a sensitive website given a packet trace? And then we also need to answer which website it is. A sensitive website would be, for example, politically, religiously, legally sensitive, and it would be a positive classification for this classifier. So this is the open world setting, which is more realistic than the closed world setting, and it becomes a hybrid binary multi-class problem. You can answer those two questions together with the same machine, of course. Because of those two challenges, we are going to be using slightly different terminology. So let's review the terminology. The first, of course, is, let's say we have a classifier that's going to be monitoring political sites. And if the user is actually visiting a political site, we're going to say yes, then that is a true positive. That is what we want. If they're not visiting a political site, such as a puppy's website, which is usually not political, we're going to call it a false positive. If they are visiting a different political site to the one that we classify it as, then we're going to call that a wrong positive. In the literature, there are also other terms for this. Some previous work has mixed together wrong positives and false positives. This is actually incorrect. This will cause a significant error in the calculations, which we'll show later. Okay, so we are going to now try to answer two important problems to motivate our work. The first is whether we prefer precision or recall. Now, of course, naively, ideally, we will want to have both. But if we have to make a choice, which one should we prefer? Previous work achieve high recall, and our results show that they don't achieve good precision. So state of the art is high recall, low precision. For website fingerprinting, this is not really a good state because think about the boy who cries wolf, for example. The boy who cries wolf achieves 100% recall because when the wolf comes, he does actually cry wolf, but his precision is so low that his positive classifications are meaningless. Everybody's going to ignore the positive classifications, so such a high recall, low precision classifier gets eaten by the wolf. And similarly in website fingerprinting, we can't use any of these positive classifications. For high precision, low recall, we have a better situation. Even though there's low recall, the positive classifications are still trustworthy, and the low recall will still capture some of the positive accesses. Because no previous work has achieved this, we're going to make this our goal. And the reason why this is a good situation for website fingerprinting is essentially because of what a positive actually is. So what is a sensitive web page? Let's look at the realistic attacker and what they might want to identify. Such likely candidates could be web pages that reveal personal behavior, private web pages that reveal what your inclinations are, such as political web pages. You're likely going to visit such web pages multiple times. You're not just going to do it once. So even a low recall would eventually capture such a pattern, even though it wouldn't capture how many times or when exactly you visit such pages. Another possibility is if such a web page has a very high risk if you're detected visiting them. So for example, if it is a whistleblowing website and you are using website fingerprinting, you're being detected as visiting a whistleblowing website, and let's say 1 hour later a bunch of documents got leaked, then they will really suspect that you are the person who leaked these documents, and you would have personal consequences. So in such a case, low recall will still be quite frightening, and it will still encourage a user to try to defend against website fingerprinting. So that achieves the goal of creating a threatening website fingerprinting attack. So that's why we believe low recall is still a threatening attack for website fingerprinting. Unlikely candidates for sensitive web pages may include home pages of top sites, utility websites such as search engines, and social media sites. Because website fingerprinting can't see what you're searching for, they can't see what you're tweeting, for example, the fact that you visited those sites doesn't tell the attacker much. So what that really says is that the base rate of sensitive web page accesses is actually going to be quite low. So that also informs us as to how we should calculate precision. We can't use the naive way of calculating precision. So what do we mean here? Let's look at the more fun example. Suppose Bob has created this Cat Finder 3000 and he's testing it against a bunch of pictures that he has. He's going to use this to identify whether or not a picture is a cat picture. So on the left, this picture looks quite like a cat picture. It is a cat picture, although it looks quite like a dog picture. It is a cat, and the Cat Finder 3000 says it is. That's good. On the right, it is not a cat, and the Cat Finder 3000 says it's not a cat. So, okay, this classifier is pretty good. It achieves 490 true positives and 20 false positives. And Bob is going to say, okay, I know that positives, the precision is calculated as the fraction of positives that are true. So I'm going to plug in those numbers and get a precision of 96%. Is this correct? This is not correct. This precision is essentially meaningless. It is not calculated correctly. How should he really calculate precision? He should be using the positive rates rather than the actual number of positives in his precision, in his experiment. And the reason why is essentially because the number of true positives in the experiment is not an approximator for the real number of true positives, whereas the true positive rate in the experiment is an approximator for the real true positive rate, and vice versa for false positives. If you use the rates, then you also need to multiply a factor to the false positives. We call it the R factor, and that is the ratio of non-sensitive events to sensitive events. Now, if, for example, in a real data set, there are 100 non-cat pictures for every cat picture, then R is equal to 100. And if you plug in those rates, then you'll get a precision of 20%, which is a far cry from the 96% we got earlier. This is quite low precision. This mistake has been made in a lot of previous work, even including my own work on website fingerprinting, and even also other problems where you want to calculate precision. And if you do make this mistake, that you're implicitly assuming R is equal to 1. But for website fingerprinting, it turns out realistic R is going to be closer to 1,000 than 1. So what you're going to get is a precision that is a far overestimate. So the formula is the following, and if we incorporate the wrong positive rate, we also get this. That's why we don't want to mix wrong positives and false positives, because wrong positives don't get the multiplier of R. And since R is very large, that creates a huge difference. Now, since R is very large, the R times FPR factor is going to dominate the precision. And that actually causes certain problems because of uncertainty propagation in the denominator, where we want FPR to be very close to 0, but FPR has an error on it. So in order to make a conservative lower bound for the precision, we're going to calculate the maximum false positive rate according to a 95% confidence interval, where we plug in Z is equal to 1.96, and N is the total number of negatives, and then we get a lower bound for the precision. If we want a tight bound, then we should increase N, which is the number of negatives. And of course, we want to decrease the real false positive rate as well. So we see that we want to discourage false positives in order to get a good precision. And we're going to use methods to increase the precision of known website fingerprinting attacks rather than come up with our own, because we want to show that this is possible. We can always do this for known attacks. The first idea is we're going to measure the confidence of all the classifiers and only accept highly confident positive classifications. The second idea is we're going to use clustering to supplement our supervised learning methods. And the third idea is we're going to use multiple classifiers to ensure that our positives are truly correct. So let's look at each of those ideas in turn. The first idea, confidence-based methods. We found that all machines can be adapted, or at least all machines that are used for WF can be adapted to also output the confidence of classification. For some, it's obvious. For some, for example, SVM is not so obvious. So let's look at SVMs. SVMs find an optimal hyperplane to separate two classes. So we're going to define the confidence as the distance to that hyperplane. And so low distance, which is to say low confidence points, will be classified as negatives. And actually what we're doing here is we're essentially moving the hyperplane towards the positives a bit so that we get more negative classifications so that there will be fewer false positives. The second idea is distance-based methods. And so let's define a distance metric, and we plot all the points. Let's say here we already plotted all the points based on that distance metric, although it doesn't have to be Euclidean. If a point would have been considered positive by the classifier, but many of its neighbors by the distance metric are negative, then we still say it's going to be negative. In this case, the distance would override the classifier for a positive classification. And the interesting thing about this is that the metric is not necessarily related to the classifier. So you're essentially getting two information sources, one from the metric and one from the classifier, and they can be based on totally different feature sets. The third idea is, instead of two sources of information, why don't we have 5 sources of information? So we have 5 classifiers, and we say we want unanimous agreement between those classifiers for a positive classification. So positives, which are sensitive websites, let's say that these 5 classifiers all say they're sensitive, but actually one of them says it's a different sensitive page. We're still going to say this is a non-sensitive web page. So and that is going to be the conclusion, because we want to be really, really sure before we make a positive classification. So this is the simplest idea, and actually this one turns out to work really well as well. So here are the results. Under R equals 1000, which is based on our data, quite a realistic range for what the base rate would be. Under R equals 1000, we can see that all previous work achieved very low precision. That is expected because they were never evaluated or adjusted for low precision. We're going to do that. And based on our best methods, using confidence-based and distance-based methods, we get such improvements to their precision. For HAKFP, which uses the confidence-based method, we get a 40 times increase up to 86% precision. And we decrease the recall down to about 38% in this case, which is quite acceptable. Actually, for this case, we don't even have any false positives in our data set, but we still can't report a 100% precision because, of course, of the conservative Wilson's method. The best competitor for this is Suriname et al.'s deep fingerprinting method in 2018, which achieves 40% precision. It's much better than the other methods, but of course, still doesn't. It's still about 6 times lower in precision than our method. And we also have another result for ensemble learning, which is 85%. So I actually especially like the ensemble learning result, so I'm going to describe it in further detail. The ensemble learning result is we just get a bunch of classifiers and we want them to unanimously agree before any possible classification. The best single classifier is WKN. And if we want the best 2 classifier ensemble, then we add HAKFP onto it. In this case, we actually already get a pretty good precision. We get already more than 10 times increase to a 40% precision. And if R is lower, then this precision would actually be even higher. So the 2 classifier ensemble could actually be pretty good for lower values for R. If we want the best 3 classifier ensemble, that's actually adding PASVM, but we want PACumul here in order to make for the best 4 classifier ensemble, we will add BIX core, which is BCS et al.'s attack from almost 20 years ago. This is actually quite an interesting attack because by itself, it doesn't have very good recall or precision, but it seems to classify things in such a unique way that its information is important and is able to distinguish certain false positives that no other classifier can distinguish. So it's actually a very nice addition to the to increase precision. We don't need 5 classifiers here because basically PASVM uses a classification method that's quite similar to PACumul, and so it doesn't really give us more information. So the nice thing, of course, about this result is there's no parameterization. It's just 4 or 5 classifiers. So main takeaways of this paper, we measured precision in WF attacks, and we found that because previous work didn't incorporate the base rate, which is generally very, very low, corresponding to a very, very high R, precision has been calculated incorrectly. And in actuality, the precision of all known WF attacks has been quite low. So we developed methods to increase their precision using our ideas. And we find that in the best case, we can increase precision by more than 40 times to at least 0.86 under R equals 1000. It's actually more than 6 times compared to the best previous work. So this has been high precision open world website fingerprinting. I'm Tao Wang, and if you have any questions, feel free to ask me at this email. Thank you for listening to my talk. I hope it's been fun, and goodbye.